In this experiment, you'll be investigating the regioselectivity of hydration across the carbon-carbon double bond of an unsymmetrically substituted alkene. In alkene hydration, the elements of water, H and OH, are added across the carbon-carbon double bond of an alkene. There are always two possible directions of addition of H and OH across the carbon-carbon double bond. One where the H becomes attached to the carbon on the left and the OH becomes attached to the carbon on the right, and another where the OH becomes attached to the carbon on the left and H becomes attached to the carbon on the right. When the alkene carbon-carbon double bond being hydrated is symmetrically substituted, as shown here, both directions, or modes of addition, afford the same alcohol product. These two structures are identical. However, when the alkene undergoing hydration is unsymmetrically substituted, when the carbon-carbon double bond is unsymmetrically substituted, as is the case in this monosubstituted alkene, the two possible modes of addition lead to isomers, different products. These are not identical. These are isomers, specifically referred to as positional isomers, or more commonly called regioisomers. The goal in this experiment is to establish the direction or mode of addition of the elements of water across the carbon-carbon double bond of an unsymmetrically substituted alkene by isolating the alcohol product and identifying which isomer, which regioisomer was afforded. Before we go any further, let's clarify what is meant by the term hydration and compare it to another term that it's often confused with, hydrolysis. So what's the difference between hydration and hydrolysis? Hydrolysis involves bond cleavage. The word ends in lysis. Recall that cell walls undergo lysis, that's cleavage of their cell wall membranes. And in hydrolysis, that is to say hydrolysis, a chemical bond is cleaved with the elements of water, H and OH, becoming shared between the two fragments, as shown here. It can be classified as a substitution reaction, and you'll see a lot of examples of hydrolysis reactions in the second semester organic lecture course. In hydration, the overall transformation involves the combining or addition of the elements of water, H and OH, to the chemical structure. So it's classified as an addition reaction. In alkene hydration, the overall transformation is addition of the elements of water, H and OH, across the carbon-carbon double bond. Please note that H and OH don't literally come from the same molecule of water. They come from different sources, as you'll see when examining reaction mechanisms. Three common laboratory methods for alkene hydration are shown here. One method involves heating the alkene and water in the presence of a catalytic amount of an acid, referred to as acid-catalyzed alkene hydration. Another method involves first treating the alkene with borane in THF solvent and then oxidizing the resulting organoborane with hydrogen peroxide in the presence of hydroxide base. This is called hydroboration oxidation. A third method involves treatment of the alkene with a stoichiometric amount of sulfuric acid, not a catalytic amount, to afford alkyl hydrogen sulfate intermediates that are then hydrolyzed to afford the alcohol product. This is the hydration method you'll use for this experiment. The mechanism of the reaction in this experiment involves the formation of a short-lived species with a positive charge on carbon called a carbocation. When an alkene encounters a proton, the proton acts as an electrophile, and the carbon-carbon double bond, specifically the pi cloud of the carbon-carbon double bond, the two electrons in the pi cloud here are illustrated by these two red dots, acts as a nucleophile. When the electrophilic proton bonds to one of the carbons of the carbon-carbon double bond, it uses the pair of electrons from the pi cloud. In this case, this proton is forming a bond to the carbon on the left. Here's the new CH bond. That leaves this carbon electron deficient, and it becomes a carbocation. The carbocation is a planar species, and the carbon is sp2 hybridized. It has an empty p orbital. Therefore, it's electrophilic, and it can bond with nucleophiles, as shown in this illustration. Here, the nucleophile has a pair of non-bonded electrons it's using to make a bond to the carbocation, and here is the new carbon nucleophile bond. So you can see that overall you've done an addition of H and Nu across the carbon-carbon double bond of the alkene. The H came from the proton source, and the Nu portion came from atoms, or an atom from the nucleophile. There are four general types of carbocation, all of which are shown here. In general, for alkyl substituted carbocations, the greater the number of alkyl groups attached to the positively charged carbon, the more stable, that is lower in energy, that cation is, and therefore the easier it is to form. Lower energy mechanistic intermediates are easier to form than those that are higher in energy. The positively charged carbon of a tertiary carbocation is attached to 3 alkyl groups, and the positively charged carbon of secondary carbocations are attached to 2 alkyl groups. Tertiary and secondary carbocations are commonly encountered as mechanistic intermediates in organic reaction mechanisms, while primary carbocations and methyl carbocations are way too high in energy to form in solution phase organic reactions, which are the type of reaction you'll encounter in your organic chemistry courses. And you should avoid proposing formation of methyl and primary carbocations as mechanistic intermediates in any of the reaction mechanisms you're asked to propose. In general, if a reaction can follow any other mechanistic pathway that avoids formation of a methyl or primary carbocation in favor of a mechanistic pathway involving formation of a secondary or tertiary carbocation, it will certainly follow the latter pathway. When a carbocation forms upon protonation of an unsymmetrically substituted alkene, it's possible that the proton could form a bond to either the most substituted carbon of the carbon-carbon double bond or the less substituted carbon of the carbon-carbon double bond. And it's always going to be the latter case, because that will afford the most highly substituted carbocation. And in general, the more substituents you have attached to the positively charged carbon, the lower in energy it is, the more stable it is, the easier it is to form. Therefore, a tertiary carbocation, which has 3 R groups attached to the positively charged carbon, is lower in energy, easier to form, more stable than a secondary carbocation, which has only 2 alkyl groups attached to the positively charged carbon. And in turn, secondary carbocations are more stable than, easier to form than primary carbocations. And in general, the mechanisms that you will see this year in organic chemistry, primary carbocations will normally be too high in energy to form. In organic reaction mechanisms, you'll frequently encounter carbocations as mechanistic intermediates, and when you encounter them, you'll see that they have 3 possible fates. As you saw previously, the carbocation is an electrophile. It's a very good electrophile, and it can easily form a bond with a nucleophile using the lone pair of electrons from the nucleophile to make a new carbon nucleophile bond. The nucleophile can be anionic, like a halide, or it could be neutral. For example, it could be a molecule of water, or an alcohol, or ammonia, or an amine. A second possible fate of a carbocation would be loss of a proton on the carbon next door to the carbocation and formation of a alkene, a new carbon-carbon double bond, an elimination process. In this case here, you can see that this hydrogen is being abstracted, and the two electrons in this carbon-hydrogen bond are being used to make a new carbon-carbon pi bond. The third possible fate would be the rearrangement of that carbocation to another carbocation of similar or greater stability. So it would never rearrange to a carbocation of lesser stability, only to a more stable or a carbocation or one that has a similar energy. In this case here, this hydrogen, along with the pair of electrons highlighted in red, migrates together over to the carbocation, making a new CH bond and generating a different tertiary carbocation. If rearrangement of one carbocation to another carbocation of similar or lower energy is possible, it certainly will occur. For example, secondary carbocations will completely rearrange to tertiary carbocations, and it's also possible for a secondary carbocation to rearrange to another secondary carbocation, or a tertiary carbocation to arrange to another tertiary carbocation, as you saw in this example here. In the latter two cases, this can occur either with some or all of the original carbocation molecules undergoing rearrangement. These two carbocations, secondary to secondary and tertiary to tertiary, are of similar energy, so there is not as great a driving force to completely convert all of the carbocation molecules of one type to another. So rearrangement could be partial. Once a carbocation forms, of course, it has the same possible fates of any carbocation. So this newly formed carbocation could be trapped by a nucleophile. It could lose a hydrogen on a carbon next door to form an alkene, or it could rearrange to another carbocation. So the rearrangements could continue. Although it's possible to perform an alkene hydration using dilute aqueous acid, in your experiment, you will be performing an alkene hydration using relatively concentrated sulfuric acid, and you'll be using a stoichiometric amount of it. Let's compare the mechanisms for these two different alkene hydration reactions. On this page will be the mechanism for acid-catalyzed alkene hydration, which occurs in dilute aqueous acid. A catalytic amount of acid is used, so the molar amount of this acid is relatively small compared to the number of moles of alkene that are present. The alkene is protonated and you form a carbocation. The carbocation can then be trapped by a nucleophile. Remember, this acid is very low concentration, so therefore the anion will be in very low concentration compared to water. Remember, this is dilute aqueous acid, so there's a lot of water present. Therefore, this electrophilic carbocation could easily be trapped by nucleophilic water. Remember, oxygen has lone pair electrons that can be used to trap the carbocation. Here you can see that this red lone pair of electrons is being used to form a bond between oxygen and this electrophilic carbon. Here's the new carbon-oxygen bond, and you end up with this second mechanistic intermediate with oxygen being protonated. Oxygen has a positive charge. Therefore, this oxygen-hydrogen bond is rather weak. The oxygen is pulling at the electrons in this oxygen-hydrogen bond, making that hydrogen acidic. So some very weak acid, like another water molecule, could come and remove this proton. These two electrons then go back to oxygen. Here you can see that the acid is truly a catalyst. We used this H+ to protonate the alkene, and now we lose a proton back to solution, so the acid is being regenerated, the H plus is being regenerated. You finally end up with this alcohol product, and you can see that overall you've added the elements of water across the carbon-carbon double bond. The H came from the acid catalyst, and this OH, the hydroxyl, came from a molecule of water. So this would be the mechanism for alkene hydration under acid-catalyzed conditions. Now, let's compare the mechanism we've just looked at with the mechanism of the hydration reaction you'll perform in this experiment, which uses relatively concentrated acid. The process can be divided into two parts, where the first part involves the preparation of an alkyl hydrogen sulfate compound by addition of the elements of H2SO4 across the alkene's carbon-carbon double bond. In the first mechanistic step, the carbon-carbon double bond of this generic alkene is protonated to afford a carbocation. Since the concentration of water is relatively low compared to sulfuric acid, remember you're using relatively concentrated acid, only a small amount of the electrophilic cation is nucleophilically trapped by water as the nucleophile, and the bulk of the cation is instead trapped by the HSO4 anion as the nucleophile to afford the alkyl hydrogen sulfate shown here. You can see that this is classified as an addition reaction, where the elements of H2SO4, H and SO4H were added across the carbon-carbon double bond of the alkene. The second part of this process involves hydrolysis of the alkyl hydrogen sulfate to afford the alcohol and sulfuric acid as products. The first mechanistic step involves cleavage of this CO bond by an SN1 process. A large volume of water is added, and HSO4-, which is a good leaving group, leaves to afford this cation upon CO bond cleavage. It's the same cation formed earlier, but now, since there's a relatively large amount of water present, instead of being trapped by the HSO4- anion as the nucleophile, it combines with water as the nucleophile to form a new CO bond. Removal of a proton from the positively charged oxygen affords an alcohol and sulfuric acid as products. You can see that overall you've added the elements of water across the carbon-carbon double bond in an alkene hydration. And you can also recognize the second part of this two-part process as a hydrolysis, where the elements of water, H and OH, are now shared between the two fragments formed upon CO bond cleavage. Recall that for this experiment, your goal is to experimentally establish the regioselectivity of the hydration reaction of the unsymmetrically substituted alkene 1-hexene using reaction conditions just described. 3 possible constitutional isomers of a hexanol could form that differ only in the position of the hydroxyl group on the carbon chain. These types of constitutional isomers are often called regioisomers. Formation of 1-hexanol would result from what is referred to as anti-Markovnikov or non-Markovnikov addition of the elements of water directly across the carbon-carbon double bond of 1-hexene, where the hydroxyl group ends up attached to the less substituted carbon of the carbon-carbon double bond, labeled number 1. Formation of 2-hexanol would result from Markovnikov addition of the elements of water directly across the carbon-carbon double bond of 1-hexene, where the hydroxyl group this time ends up attached to the more substituted carbon of the carbon-carbon double bond, labeled number 2 here. 3-hexanol would result from rearrangement of the secondary carbocation that's formed directly upon protonation of carbon number 1 of the alkene to another secondary carbocation on the adjacent carbon labeled number 3. You'll establish the regioselectivity of the reaction by identifying the isomers of product that form. This you'll accomplish by co-spotting on the same TLC plate your reaction product along with authentic samples of the 3 possible hexanol isomers. The technique of TLC co-spotting is described in a separate video. Although one major hexanol isomer would be expected, a mixture of products could result. You should be able to provide a feasible mechanistic explanation for the outcome of this reaction and become familiar with the modes of formation and the reactions of carbocations.